Hello, class. Our next section's on section 1.7, population models. And for the population model, we would suppose the population changes by only births and deaths. So we will define beta of t to be the number of births per unit of population per unit of time at time t. And little delta t is the number of deaths per unit of population per unit of time at time t. The number of births and deaths occurring during the time interval, the closed time interval, t, t plus delta t, is births being beta of t times p of t for the population times delta t, and deaths delta t times p of t times delta t again. The change delta p is the population during the time interval of length delta t. And we could calculate that change in p population by taking the births and subtracting the deaths. So using our two functions that we just defined, that allows us to write it as that change in the population with respect to time is approximately beta of t minus delta of t times p of t. The error should approach 0 as delta t approaches 0. So we could take then the limit to yield the derivative of p with respect to t is equal to beta minus delta times p. Well, beta is beta of t, delta is delta of t, and p is p of t as the general population equation. If the birth and death functions are constant, we get the natural growth equation. And when it comes to these, we obtain, we first have this example here. So suppose that an alligator population number is 100 initially, and that its death rate is delta is equal to 0. If the birth rate is beta is equal to 0.0005 times p, we want to give the associated initial value problem. So from what we just saw, the derivative of p with respect to t is going to be 0.0005 times p squared, with p of 0 being 100. And then we could solve it, right? By separating these variables. We could, in this case, divide by p squared, multiply by dt. So we would get dp over p squared is equal to 0.0005 dt. And then integrate both sides. The left side makes -1 over p. And the right side makes 0.0005 times t plus c. If we put 0 in for t and 100 in for p, we would obtain the value for c to be -1 over 100. So this equation then becomes -1 over p is equal to 0.0005 t minus 1 over 100. And then we could solve for p to get our function p of t to be equal to 2000 divided by 20 minus t. And we could see as we approach the value of t of 20, which we could also see here on the slope field, our population p of t is approaching positive infinity, as we could see happening on this particular slope field. So that means there is indeed a what we could refer to as a population explosion happening around 20 years, which, is not exactly a a real-life scenario due to the fact that there's always limits in populations and whatnot. And based upon that, we have these bounded then populations. And this is caused from a common phenomenon of the birth rate decreasing as the population increases. So we suppose the birth rate is a linear decreasing function of beta is equal to beta sub 0 minus beta sub 1 times p, where the death rate remains constant, delta is equal to delta sub 0. Then the derivative of p with respect to t is equal to beta sub 0 minus beta sub 1 times p minus delta sub 0 times p. That makes a times p minus b times p squared, where a is b sub 0 minus delta sub 0, and b is beta sub 1. For a and b as both being positive, this is then a logistic equation, and we can express this as the derivative of p over t is equal to k times p times m minus p. K is equal to b, and m is a over b. So, for example, back from section 1.3, example 4, we obtain the logistic equation derivative of p with respect to t is equal to 0.00004 times p times 150 minus p is equal to 0.06p minus 0.0004 p squared. And we want to solve this differential equation. So, utilizing the not simplified version, we could separate this by dividing by p times 150 minus p and multiplying by dt. So we are going to get dp over p times 150 minus p is equal to 0.0004 times dt. And we're going to integrate both sides. The thing, though, is we need to use partial fractions due to this left-hand side. So partial fractions. So I'm going to express this as 1 over p times 150 minus p. Using partial fractions, we can write this as equal to 1 over 150 times 1 over p plus 1 over 150 minus p. So this left-hand side, utilizing the partial fractions and taking out our constant 1 over 150, we get this 1 over 150 times the integral of 1 over p plus 1 over 150 minus p dp is equal to the integral of 0.0004 dt. The left side is going to make 1 over 150 times the natural logarithm of the absolute value of p minus the natural logarithm of the absolute value of 150 minus p. And this is going to be equal to 0.0004 t plus c. We could multiply by 150 to give us the natural logarithm of the absolute value of p minus the natural logarithm of the absolute value of 150 minus p to be equal to 0.06 times t plus some constant c. We can simplify this left-hand side because we have all these natural logarithms. And that is going to become the natural logarithm of the absolute value of p divided by 150 minus p is equal to 0.06 times t plus c. And we then can now use all of these then as powers of e. This left side just becomes p over 150 minus p is equal to, this would be e to the c power times e to the 0.06 times t power. And we could express this as b times e to the 0.06 times t power, where b is equal to e to the c power, since it's just a constant. And these are actually positive, can be positive or negative. So let me include that here first before continuing. So positive and negative e to the c power. If we substitute in the value of t equaling to 0, and we let p be some number, p sub 0, but it cannot be 150 due to a denominator, and we can't divide by 0. So that means the value for b is going to be equal to p sub 0 divided by 150 minus p sub 0. And then we could write our equation here as p divided by 150 minus p is equal to p sub 0 times e to the 0.06 times t power divided by 150 minus p sub 0. But we could then solve for p to obtain the following equation. I'll write that right here. P of t is going to be equal to 150 times p sub 0 divided by p sub 0 plus 150 minus p sub 0 times e to the negative 0.06 times t power, once we simplify everything. And we could see that if we take the limit as t approaches infinity, and we could see that here in this picture down here as well. Limit as t approaches infinity of the function we just wrote, p of t. No matter what p sub 0 is, it could be a big number, a small number. No matter what, though, notice as we let t approach infinity, all of these eventually approach 150 based on our population carrying capacity. So with that being said, the solution of the logistic value problem, the derivative of p with respect to t, is equal to k times p times m minus p, and p sub 0 is equal to p sub 0. So that would be equal to p of t is equal to m times p sub 0 divided by p sub 0 plus m minus p sub 0 times e to the negative k times m times t. And that'll be positive. And if p sub 0 is equal to m, we have the equilibrium population equivalent to equaling to m. If p sub 0 is between 0 and m, then once we go through our calculation, we eventually have a positive number instead of our denominator here, which is going to mean that the logistic equation that we just saw in the last slide, that would be less than a value of m. If p sub 0 is greater than m, then our logistic equation is going to have a negative number inside of it, and that means it's then going to be greater than our value of m. The positive or negative number in this denominator has an absolute value less than p sub 0, so it approaches 0 as t approaches infinity, which causes a limit as t approaches positive infinity to be equaling to m. And we could refer to that m then as the carrying capacity due to that, and we could see what happens no matter what value of p sub 0 we have, we eventually approach the value of m. As another example, let us suppose that in 1885, the population of a certain country was 50 million and was growing at a rate of 750,000 people per year at that time. Suppose also that in 1940, its population was 100 million and was then growing at the rate of 1 million per year. Assume that this population satisfies the logistic equation. We want to determine the limiting population m and predicted population for the year 2000. So we would need to use the values of, we are going to express the 750,000 as 0.75. This is going to be equal to 50 times k, due to this 50 million, times k, times m minus 50. And this, again, is because we are using a unit of a million. So let me just write that here. And the other one that we can make is 1, due to the 1 million, is equal to 100 times k, due to the 100 million, times m minus 100. And we could solve this simultaneously and obtain our two values. We could obtain m being equaling to 200 and k being equal to 0.0001. And so, because of that, the limiting population is going to be 200 million. In this particular case. So, for this, we wanted to also find the predicted population for the year 2000. And so, before doing anything, we need to first express that for t is equal to 0, this being for 1940, we know that we would get a value of p sub 0 to equal to 100. So, the year 2000 would indicate a value for t to be 60. So to plug that into the logistic equation, we get p of 60 is equal to, this is going to be 100 times 200 divided by 100 plus 200 minus 100 times e to the power of negative 0.0001 times 200 times 60. If we toss that into a calculator, we should get an answer of about 153.7 million people. For the next example here, I have the United States population in 1800 was 5.308 million, and in 1900 it was 76.212 million. If we take p sub 0 to be 5.308, we want to build that natural growth model. We could see that 76.212 would be equal to 5.308 times e to the 100 times r power, which means we could then yield r to be 1 over 100 times the natural logarithm of, this would be 76.212 divided by 5.308, whatever that makes. And when we toss that into a calculator, you'll get an answer for r to be about 0.026643. Which means then the logistic, the natural growth model that we would obtain for this would be P of t is equal to 5.308 times e to the power of, in this case, 0.026643. Times t power in this case. For example 5 of the US population in 1850 was 23.192 million. And if we take p sub 0 to be 5.308 and continue with the work we just did in example 4, then for this, we need to do a couple of things. Based on this 1850 and 23.192 million, that means that p sub 0 would be equal to 5.308. T would be 50. And P would be 23.192. And for the 1900 that we had, so this is for 1850, for 1900, we would still be using, we'll be using for this then a value of t of 100 and a value of p as equal to 76.212. So for this, we would have two equations. First one is going to be 5.308 times m divided by 5.308 plus m minus 5.308 times e to the negative 100 times k, negative 50, not 100. Negative 50 times k times m power. and this is supposed to be equal to 23.192. The other equation that we have is 5.308 times m divided by 5.308 plus m minus 5.308 times e to the negative 100 times k times m power, and this would be equal to 76.212. And so now we have those two variables again, k and m, that we need to solve. But we could certainly solve this, and we could solve it nicely without the needing of a computer algebra system. We could get the value of k to be 0.000167716, and the value of m to be 188.121. And because of that, then we could then build our equation as the following. 998.546 divided by 5.308 plus 182.813 times e to the negative 0.0315551 times t power. And then we could see this graph down here. The one that we did previously in example 4 is this function here, and then the logistic equation that we just made is right here. And do note the errors that start building based on that. And we have a couple more applications involving this logistic equation that we have for the population model. First and foremost, we would obtain, based on those errors, an average error being the square root of the average of the squares of the individual errors. And a couple of applications include limited environment situation. This is an environment can support a population at most m individuals. The growth rate beta minus delta is proportional to m minus p for further expansion. Thus, beta minus delta is equal to k times m minus p, and the derivative of p with respect to t is beta minus delta times p is equal to k times p times m minus p. For a competition situation, that's where the birth rate beta is constant, but the death rate delta is proportional to p. Thus, delta is equal to alpha times p, and the derivative of p with respect to t is beta minus alpha times p, that being k times p times m minus p. And the joint proportion situation, this would be that P of t denote the number of individuals in a constant size susceptible population M infected with a disease. This is spread by chance encounters. P prime of t would be proportional to the number of individuals P infected times M minus P of those not having it. Thus, the derivative of P with respect to t is equal to k times P times M minus P. So let us suppose that time t, 10,000 people in a city with population m is equal to 100,000 people have heard a certain rumor. After 1 week, the number p of t of those who have heard it has increased to p of 1 is equal to 20,000. Assuming that p of t satisfies the logistic equation, when will 80% of the city's population have heard this rumor? So we are going to let p sub 0 equal to 10, and the value of m to be 100,000. Or I'm just going to write that as 100. So First and foremost, the equation we're going to have for this, P of t, we are going to express this as 1,000 over 10 plus 90 times e to the negative 100 times k times t power. If we put in a value of t of 1 and p of 20, we would obtain this equation. 20 is equaling to 1,000 divided by 10 plus 90 times e to the negative 100 times k power. And then we could solve this. Right. We could obtain the value of e to the negative 100 times k power is equal to 4/9, which then implies that the value of k is equaling to 1 over 100 times the natural logarithm of 9/4. Toss that into a calculator and we get an answer of about 0.008109. So if we let P of t equaling to 80, we obtain this. 80 is equal to 1,000 divided by 10 plus 90 times e to the negative negative 100 times k times t power. So we could solve this as, just like before, e to the negative 100 times k times t is going to be equal to 1 over 36. Which means that we could solve for the value of t to be equal to the natural logarithm of 36 over 100 times k. We already know what k is, so we can actually just write this as natural logarithm of 36 over 100 times k. If we just look at this value right here, we know that this is supposed to be the natural logarithm of, well, 100 times 1 over 100 times the natural logarithm of 9/4. So natural logarithm of 9/4. This will give us an answer of about 4.42. So about 4 weeks and 3 days would be how long that takes. Doomsday versus extinction is where a population P of t of animals where females rely solely on chance encounters to meet males, for example. This occurs at a rate proportional to the product of P divided by 2 of males and P divided by 2 of females, or at a rate proportional to P squared. We assume births occur at the rate K times P squared, where the birth rate is then given by beta is equal to K times P. If the death rate delta is constant, the general population differential equation is then derivative of P with respect to t is equal to K times P squared minus delta P, which is equal to K times P minus M, where M is delta over K being greater than 0. M is then the threshold population. The population's behavior depends critically on whether the initial population, P sub 0, is less than or greater than M. So as an example, consider an animal population P of t modeled by the equation derivative of P with respect to t is equal to 0.0004 times P minus 150. That being equal to 0.00004 times P squared minus 0.06 times b. And we want to find p of t if p of 0 is equal to 200 and p of 0 is equal to 100. So, as we have previously seen, we can separate these variables and obtain, we would divide by p times p minus 150, multiply by d of t. We would obtain the derivative of p divided by p times p minus 150 is equal to 0.0004 dt and integrate both sides. Then from previously, the last time we saw something like this, we used this partial fractions. It's roughly the same partial fraction. I'm not going to write out the entire step again, but we would obtain this, negative 1 over 150 times the integral of the partial fractions would be 1 over p minus 1 over p minus 150 dp is equal to the integral of 0.0004 dt. This will then, once we simplify a bit here, give us the natural logarithm of the absolute value of p minus the natural logarithm of the absolute value of p minus 150. That's equal to negative 0.06 times t plus c. Simplifying this, raising both sides to e, will give us p over p minus 150 is equal to positive and negative e to the c times e to the negative 0.06 t. And we can write that again as b times e to the negative 0.06 t power, with the value of b being equal to positive or negative e to the c power. And so based upon that, if we put into this then, the first value here of t equaling to 0, so I'll write this as 4, t equals to 0, and p is equal to 200, we would obtain the value of b of 4. Then we can then write for this that p of t is equal to 600 times e to the negative 0.06 times t power divided by 4 times e to the negative 0.06 t power minus 1. And from this, as t increases, and approaches capital T is equal to the natural log of 4 divided by 0.06, which is about 23.105. This then is then going to decrease and approach 0. Which of course would then indicate a doomsday type of idea. That being the first one here. And I'll just write the second one up here just so I have more room. But for that t being equal to 0 and p being equal to 100, b in this case is going to be equal to negative 2. So this would then make P of t is equal to 300 times e to the negative 0.06 times t power divided by 2 times e to the negative 0.06 times t plus 1. Which would give us then 300 over 2 plus e to the 0.06 times t power. And this time for this, if we have t increasing without bound, then this population will be ever increasing. So p increases. So based upon this, excuse me, I should probably actually note something here. If t is increasing without bound, then this denominator here is increasing without bound. But then that also, then again, will show a population approaching that value of 0 again. So showing yet another form of that distinction-based consequence. And we could see that in our graph down over here on the bottom right. Let me know if you have any questions or concerns. Thank you.